Another type of optimization problem is network modeling. So some business problems can be represented graphically as networks. And some examples of these types of business problems include transshipment problems, shortest path problems, maximal flow problems, generalized network flow problems, and so on. And you'll see that how we structure these problems using a tool like Solver is a little bit different than the problems that you've structured using Solver so far. But nonetheless, Excel Solver can help you find optimal solutions or evaluate different scenarios or approaches to each of these problems. So network flow problems can be represented as a collection of nodes connected by arcs. So these tend to be problems that we can sketch out very visually. We have three types of nodes. We have supply, demand, and transshipment nodes. And this is a scenario where we might actually see negative numbers in our problems. So far, negative numbers have tended to be something that we don't see a lot of and we don't interact with because we've looked at production and it's not really a thing to produce negative numbers of things. So this is a visual example of a transshipment problem, and here you can see the nodes and the arcs and how we can sketch this problem out. So in this example, the Bavarian Motor Company transports vehicles to the ports in Jacksonville, Florida, and Newark, New Jersey, 200 vehicles to Newark, and 300 vehicles to Jacksonville, and then they need to distribute them among their network of dealers in Boston, Richmond, Atlanta, Mobile, and Columbus. And what we see on each of the arcs is the cost to ship a single vehicle between those nodes. So for example, if you're shipping from Jacksonville to Richmond, the cost is $50. And then next to each node, we see the demand. So for example, there's a demand for 80 vehicles in Richmond. There's demand for 60 vehicles in Columbus. And we also see that there are some nodes where vehicles can be transported in either direction, but the price to transport in opposite directions is not necessarily the same. For example, we can take a look at Atlanta and Mobile, and to ship from Mobile to Atlanta is $25, but the opposite from Atlanta to Mobile is $35. And then the numbers under the city names in the node, that's the number of the node. So we could refer to node 4 as, well, we could call it node 4, or we could call it Richmond. So how would we go about defining our decision variables, our objective function, and our constraints? Well, let's look at this theoretically, and then let's dig into how we would go about setting this up and solving this problem using Excel Solver. So for each arc in a network flow model, we can define a decision variable as the amount being shipped or the amount flowing from node I to node J. So for example, we could have X12 or X12, and this is the number of cars that are shipped from node 1, which is Newark, New Jersey, to node 2, Boston, Massachusetts, or X56, the number of cars shipped from node 5 in Atlanta to node 6 in Mobile. So those subscripts on those X's are generally the node from and the node to. And in this specific problem, we have 11 node pairs. So our objective here is to minimize the total shipping costs. The Bavarian Motor Company wants to get their vehicles to market, but it wants to do it as efficiently as possible. So while many problems we've worked with so far have involved maximizing profits, in this scenario we want to minimize our shipping costs. And we express this mathematically with the equation that you see. So for example, that first item, 30x12, 30 is the cost of transporting a vehicle from node 1 to node 2. So 30 is the coefficient, and then x12 is the number of vehicles that we are transporting between node 1 and node 2. And the same applies for the rest of the items in our equation. And this might look a little bit intimidating. Once we pull it into Excel though, I think the idea might start clicking just a little bit better. So for network flow problems, we have to consider these balance of flow rules. In this scenario, we're working with a minimum cost network, and it's important to determine if the relationship between the total supply and the total demand. In some problems, your supply is going to exceed your demand. In others, your supply may be less than your demand. It's a little bit of a problem. And then in some scenarios, your total supply and your total demand will be equal to each other. Depending on the scenario, you will consider a different balance of flow rule at each node. In this specific scenario, we have a little bit more supply than demand. So we would use that first balance of flow rule where the inflow and outflow is greater than or equal to the supply or demand at each one of the nodes. So let's take a look at our constraints. Like I said, our total supply is 500 cars, but our demand is only 480 cars. So this means that our supply is just a little bit greater than our demand. So that means that in each node we need a constraint like this, where the inflow minus the outflow should be greater than or equal to the supply or demand at each node. So for example, the constraint for node 1 would be minus x12 minus x14 is greater than or equal to minus 200. And it's important to note that there's no inflow for node 1. Node 1 only transmits vehicles out. There are no vehicles being sold at node 1. This is equivalent, however, to x12 plus x14 being less than or equal to 200. And if that isn't quite gelling, the example is described in great detail in the text, and once we convert this and put this into Excel, I have a hunch it's going to make just a little bit more sense. So defining our overall flow constraints, it looks a little bit like this. And you're probably thinking, wow, that's a lot. But we have to have a constraint for each of our nodes, and then it is also worth noting that for node 1 and node 7 we see the negative signs. And again, this reflects those nodes where the vehicles are received but that have no demand for those vehicles. So in Newark, New Jersey, node 1, and Jacksonville, Florida, node 7, they receive 200 and 300 vehicles respectively, but there's no demand for them there. So from those nodes, we need to shift them to nodes 2 through 6. We also know that there is a non-negativity condition. We're not destroying any vehicles or disassembling any vehicles. It is known that sometimes when vehicles are shipped overseas, on large ships, for example, it's not unknown for a few of them to just fall overboard. But in this scenario, our vehicles have landed at the ports of Newark and Jacksonville, so we don't need to worry about a vehicle or two falling off the side of a ship. So now let's take a look at getting this input into Excel. There is a blank version of this Bavarian Motor Company example in eCampus, and I suggest that at this time you open that up in Excel. So here we have our example opened up in Excel, and like every other problem we've worked with so far, we have an objective cell, we have our variable cells, and we have our constraint cells. Our objective cell is highlighted with the blue text, and it looks at the sum product of B6 through B16 and G6 through G16. So what this is, B6 through B16, these are our variable cells, and they're being multiplied by the unit cost or the cost to transport each vehicle between the different nodes. And all of the potential combinations of nodes are listed here as from and to. As with prior scenarios, there is no formula in our variable cells. The variable cells are the space that we give Excel to try out different combinations of numbers to find the optimum solution. And then we have constraints that dictate some of the limitations on what can go where in terms of quantity and in terms of direction. So we can take a look at our constraint cells, and we see that we have a pretty impressive formula where we're looking at the different nodes and the capability of shipping and moving things between the different nodes using the sum-if function. So this may be a little bit more of an advanced function than you're typically used to working with in Excel. But again, the text has some great resources, and there are some resources on eCampus that will help you master some of these somewhat more complex formulas. For as daunting as these formulas look, though, they simplify the math involved for us so that we can focus on interpreting the results. And as executives and business analysts, it's most important for us to be able to look at and interpret our results. So how on earth do we go about setting this up in Solver? First, we open up Solver. Our objective cell is going to be G18, and we are trying to minimize the cost of getting these vehicles from Newark and Jacksonville to the other cities in our dealership network. So we want to make sure that minimize is selected. We're going to select our variable cells, and then we have to add a few constraints. So first, we want to make sure that our net flow is greater than or equal to our supply and demand. And this goes back to those rules that we looked at in the slides, where we consider whether our supply exceeds demand, our demand exceeds supply, or if they're balanced. So we're going to add this constraint where our net flow must be greater than or equal to our supply and demand. And again, if you're not sure which is which, refer right back to those slides and consider whether your supply is greater than your demand is greater than your supply, or if they are perfectly balanced. And then we have one other constraint, and that is the vehicle shipped. So our variable cells, B6 through B16, we need these to be greater than or equal to 0. We want to do our very best to satisfy the demand in each of our nodes. And to do that, we can't have any negative number of vehicles shipped between our nodes. So I'm going to enter 0 there. Yes, for constraints, we can do a hard constraint to a specific number, or we can refer to a specific cell. So I will click OK. And now we have our problem set up in Solver. So I'm going to click Solve. And what we see here is a total transportation cost of $22,350. We could probably add 3 more zeros to the end of that to make that the true value. And we have some important information that's made clear to us in this output in Solver. So we see that we ship all 200 vehicles from Newark. They're going to other places. We can see over here in rows 6 and 7 that 120 vehicles from Newark went to Boston and 80 vehicles from Newark went to Richmond. And 120 plus 80 is 200. So that accounts for all of our vehicles from Newark. From Jacksonville, 280 vehicles were shipped. And this makes sense because we had a surplus of 20 vehicles. So what this tells us is that we have about 20 vehicles just chilling out in Jacksonville, and maybe there'll be demand for them later. Maybe they'll be used as prizes on The Price is Right or something like that. And of those vehicles from Jacksonville, we see in rows 15 and 16 that 210 of them went to Atlanta and 70 of them went to Mobile. And then what we can see here in rows 10, 11, and 12 are how many vehicles were shipped from Atlanta to other nodes. And we see that no vehicles were shipped from Atlanta to Richmond or Mobile, but 40 vehicles were shipped from Atlanta to Columbus. And we can also see, based on vehicles that were shipped out of Newark, they went to either Boston or Richmond. We have 20 vehicles were shipped from Boston to Columbus to satisfy the demand in Columbus. And what we see in our constraint cells is that we successfully satisfied demand for all of our vehicles in Boston, Columbus, Richmond, Atlanta, and Mobile. Even if those vehicles may have come originally from different ports and different nodes, because, for example, Columbus received 20 vehicles from Boston and 40 from Atlanta to satisfy its total demand of 60 vehicles. I don't know about you, but I think this stuff is pretty cool. But if you're more of a visual learner, let's go back to the slides and take a look at what this looks like visually. So if we looked at the solution that we generated in Excel in a visual format, this is what it would look like. And we see that we don't have quite as many arcs as we did when we originally sketched out the problem and looked at all the feasible ways that vehicles could travel. It turned out that only a few specific nodes and arcs were needed. Well, all of our nodes were needed, but not all of the arcs were required. And we can see that our vehicles from Newark and Jacksonville, we can see where they all went visually. We can see that 80 of them from Newark went to Richmond, which perfectly satisfied Richmond's demand for 80 of them. Then 120 went to Boston, and Boston had a demand for 100 of them, so 20 of those were passed on to Columbus. And then we can look at Jacksonville as well, where 70 went directly to Mobile, and 210 went to Atlanta, and Atlanta had a demand of 170, so it passed 40 more of those on to Columbus. So between the contributions of Boston and Atlanta, Columbus was able to satisfy their demand for 60 of their vehicles. So many problems really boil down to determining the shortest or least costly route or path through a network. And one very practical application of this is emergency vehicle routing. If you need a fire truck or an ambulance, you want it to get to you as quickly as possible. Or if you're awaiting important medication or maybe an organ transplant, you want that to get to you pretty darn quick. And these are special cases of transshipment problems where there may be one supply node with a supply of -1 and one demand node with a demand of +1, and all other nodes have a supply or demand of 0. And the idea is moving through the nodes as quickly as possible, but you're not concerned about shifting inventory or necessarily the cost of getting from node to node to node. For example, with emergency vehicle routing, generally insurance or Medicare is billed on per loaded mile, so hitting specific nodes does not necessarily have a fixed cost associated with it. The money aspect is calculated in another approach. In some other problems, a gain or a loss may occur in flows over arcs. So for example, if we're shipping something through a leaky pipeline like oil or gas, although hopefully that pipeline isn't very leaky, that could be an environmental problem, it's important to calculate if there is going to be loss in the system. Or some very long pipelines may have junctions where additional product enters into the pipeline. One very famous example of a leaky pipeline are some of the aqueducts that take water into New York City. The original infrastructure that moves water into New York City is now well over 100 years old, and some of the pipes used to ship water from further up the Hudson Valley, well, those pipes are made out of wood, and it is impossible to get into them to service them without causing enormous interruptions to utility access in New York City. So while these systems get older and more decrepit and more water leaks out of this infrastructure, there's not a lot that can be done. However, if you are working for a utility, you really need to be able to take into account that you may be losing some product along the way. And the same thing works with some of the uncovered aqueducts in California, where evaporation has to be considered and taken into the equation. A lot of the water that comes out of the tap in places like Los Angeles tends to be very mineral heavy, and a lot of this has to do with the fact that there is evaporation as that water traverses open air aqueducts from the Colorado River. And there are other scenarios. There may be theft, Or, like I said, when you're shipping vehicles across the ocean, sometimes a few of them just fall off the ship. With food, sometimes food is spoiled during transportation, and there may also be imperfections in raw materials as they enter a production process. So there are many scenarios where there may be a gain or loss that occurs as things flow through or over arcs. And we can even kind of think about that in terms of the Bavarian motor car example, where we saw that on the way to Columbus, many vehicles were stopped in, for example, Boston or Atlanta to satisfy the demand in those places, which meant that to satisfy the demand in Columbus, they kind of had to cobble. The optimum approach was to kind of cobble things together. In generalized network flow problems, gains and losses associated with flows across each arc effectively increase and decrease the available supply. So, like I said, one of the first things that we do when we work on developing and building these network flow problems in Excel to use in Solver is we consider the relationship between the supply and the demand. And when there are scenarios where there may be gains and losses associated with flows over each arc, that can really influence which rules you use as you set up the problem in Solver. And sometimes it can make it not only difficult, but impossible to tell if the total supply is adequate to meet the total demand. When in doubt, it is best to assume the total supply is capable of satisfying the total demand and use Solver to prove or to refute this assumption. And if all demand can't be met, another objective might be to meet as much of the demand as possible at minimum cost. But that might influence how you structure your constraints in Solver. So it's not enough just to know the numbers and be a numbers person. You need to have a really good, deep, and solid understanding of the system and the business that you're working with. If it were just about the numbers, we could just make computers do this. But it's as much of an art as it is a science. So your creativity and critical thinking, that is so important alongside your ability to set up these types of numerical optimization problems in Excel. We're not just doing statistics and just doing linear programming problems. We're solving real business problems. Then in some network problems, the objective is to determine the maximum amount of flow that can occur through a network. And the arcs in these problems have upper and lower flow limits. And that can add a little bit of extra challenge in structuring these types of problems. But some examples of these scenarios where you might need to build a solution that can handle this might be determining how much water can flow through a network of pipes, how many cars can travel through a network of streets. One issue that they're running into now in California is the demand on the power grid, and the capacity of the grid and the amount of demand on the grid aren't the same values, and they fluctuate based on a variety of different variables. So these network type problems can get enormously complex, but as the complexity grows, the demand for an optimal solution and a solution that can be put into action only increases. So that's a little bit of food for thought about where we can take these types of network flow problems. That's all I have for you today. I strongly recommend that you carefully work through the Bavarian motor car example in Excel and that you really go through and dissect each one of the equations used in the objective cell as well as each of the constraint cells. I also think it would be helpful if you familiarized yourself, if you're not already familiar, with the VLOOKUP, sum problem, and sum if functions in Excel. So that's a little bit of extra work to do. Good luck, you're doing great, and I'll see you soon.